There is a third way to look at things too, which at first also seems completely unrelated. And the third has to do with it being a frequency response. So maybe a nicer way of summing this up is that our first perspective is all about seeing how it's related to the difference equation. Our second perspective is seeing how it's related to the impulse response. And the third is its frequency response. And to understand what I mean by a frequency response, there are certain things called eigenfunctions. And complex exponentials are among them, so are cosines, so are really odd things like certain Gaussian functions that you'll learn about in grad school. But if you take a eigenfunction and put it into a system, the most remarkable thing happens. What you get out is that exact same eigenfunction, unchanged, except multiplied by a constant, possibly complex constant. And the value of that constant is some sort of function of the particular eigenvalue you put in. And that's really surprising. If you put in a square wave into a linear system, you won't get out a square wave. If you put in a triangle wave, you won't get out a triangle wave. You'll get things that look fundamentally different. But if you put in a cosine wave, or you put in a complex exponential, or a regular exponential, a real exponential, you'll get out the exact same shape, just scaled. And the most common example of an eigenfunction, this is of real theoretical use, especially in graduate school, is this guy, e to the j omega naught n. You know, it's been a while since we've had a talk about Euler, so let's just talk about Euler's relationships over here. All right, so Euler's identities, just as a review, is that e to the j omega is complex. It has a real part that's cosine of omega, and it has an imaginary part that's sine of omega. And that means you can break up any cosine of omega into two complex exponentials. The first is at omega, and the second one is at minus omega, and you just need to divide it by 2. And there's something very similar for sine of omega. It looks almost the same, except we're going to divide it by j2, and we're going to subtract. Okay, now that we've got the Euler's identities, let's go back and talk about this complex exponential. So, Stone, given this, e to the j omega naught n, what's the variable that's changing, and what's the variable that's not changing? We've got an omega naught and an n. Which is the one that's changing, and which of the one is static?
Value n would be changing.
Exactly. And we usually show things that are not changing with that subscript. So we've got this omega sub naught, which means it's not changing. It means it's some particular complex frequency. And so what we're going to get out from this are two separate things. We're going to get this k, this complex number, multiplied by our eigenfunction. And our k is, bizarrely enough, our system transfer function. And we're going to evaluate it at omega naught. So this is not a waveform, a complex waveform that's varying in time. We're not looking at something that's doing, this with a real part and then something else for the imaginary part. This is a number. And this number is our complex coefficient that we had listed up here. And then we'll multiply this by our original e to the j omega naught n at that exact same frequency. Okay, so this is used all the time in grad school for theoretical derivations, but let me tell you the more practical way. If you take the real part of this, you end up with a cosine of omega naught n. And you put that into your system. And when you take the real part of this mess, you end up seeing that it's equal to some scaling factor, some amplitude, which is the magnitude of h of e to the j at that particular frequency. So this is no longer a complex number. This is a real number. And in particular, it's our amplitude. And we're going to multiply it by the exact same frequency of our input, except we know that there's going to be some phase difference. And that phase is going to be the angle of h of e to the j omega naught. So there's our phase.
Wasn't that something similar to what we did in signals with like an A to?
It's exactly what we did in signals. Continuous time, I'm going to call it. No difference at all. And so this is an amplitude, and it's a function. Shoot. This is an amplitude, and it's a function of our frequency. And this is a phase, and it's a function of our frequency. And you know from continuous time that you can make any kind of signal at all as a sum of these cosines of different frequencies. And therefore, if you know what your system does to this particular input, if you know what its amplitude is and its phases as you sweep this omega naught between its available frequencies, and Cole, what are those available frequencies? What are those unique frequency limits for discrete time?
Isn't it 0 to pi?
It's just 0 to pi. And as long, wow, this is really going everywhere. And as long as you sweep it between those two limits, you have a complete description of your system. So this is a third way that we can think about what our system transfer function is a complete description of our system is what it does to different frequencies. So if you plot the gain, amplitude, and the phase versus omega, it's just called a Bode plot. Now, in discrete time, we have a particular thing we call a gain function. And this gain function is just a fancy way of defining this, which is just a fancy way of describing this part here. And it's going to be our magnitude as we sweep that frequency around, but we're going to multiply it by 20 log base 10 so we can measure the results in decibels. And we also have, therefore, a phase function, which we'll call theta of omega, and that's just simply the angle of h of e to the j omega as we vary frequency, and that's measured in radians. It's a small difference. When we talked in continuous time, we typically measured everything in degrees, and now we're going to measure everything in radians. So these two things completely specify what h of e to the j omega is. These specify the two parts of e to the, These specify the two parts of h of e to the j omega. We know h of e to the j omega is complex. So if we take the magnitude, that's the gain. If we take the angle, that's the phase. Completely specified what h of e to the j omega is. And so yet another way of thinking about what this system transfer function is it's just a way of measuring its response to different cosine frequencies. So let me just give a quick example of how this becomes useful. Find the gain function, g of omega, if h of e to the j omega is equal to this. What does, big picture, I'm telling you what the system transfer function is. I want you to tell me what its gain function is, because that will tell you if it's a high frequency filter or a low pass filter or what it's doing in the frequency domain. And what does this look like that we talked about just before?
4 cosine of omega.
Yeah, exactly. You just did that in your head, but it looks just like those Euler identities. So that's always gets confusing to me if it's 1 cosine of omega or 4 cosine of omega. And what I literally do is I force that 1/2 out of there. And then to make it the same, I'd have to say it's 4 e to the j omega plus 4 e to the minus j omega. And now I can directly match it with what I have over here. And I can see that that is indeed, as you did just in your head, equal to 4 cosine of omega. And so therefore the gain function is going to be equal to 20 log base 10 of, this is a real mess, 20 log base 10 of all of this. So 20 log base 10 of 4 omega. Okay. Let's do another one. Find the impulse response of this system we were just talking about. So to make it clearer, this is all one example. So find h of n if
So I'm gonna just view it through.
h of e to the j omega is equal to that same thing, 2e to the j omega plus 2e to the minus j omega. And can I give you a hint to make it clearer? Tell me what h of z is to start off with.
It's 2z plus 2z to the negative first.
All right. So now go for it. What's h of n?
H of n is 2 impulse of n plus 2 impulse of n minus 1.
Almost. It's not 2 impulse of n, but it's 2 impulse of n. There's a times a z.
Plus 1.
Plus 1. Maybe I just misheard you. I don't know. But that's it. Impulse of n minus 1. Is that what you said and I just misheard you?
No, sir. I said of n.
Okay. Well, you got the hard part. We've got these 3 different perspectives, and when would you actually use each of these guys? You use perspective 1 if you're given the difference equation and you need to find anything else. You'd use the second perspective if you're given the impulse response, where you're asked to find something about the impulse response. And then the third one, if it's a frequency question, it's asking you, is this a high pass filter? Is this a low pass filter, a band pass filter, band stop filter, something like that.